This lesson is about some of the math behind electric circuits. Some of the quantities that we might want to observe or measure or calculate, as well as the units we'll use to measure them with, and the formulas that relate them to each other. And the first quantity I think we should talk about is charge, because fundamentally that's what makes an electric circuit go. Electric circuits are the movement of charge around wires. So what do we need to know about electric charge? Well, electric charge can be positive or negative. And it comes from protons or electrons. And I want to dwell on this for just a second. Sometimes students at this stage will understand that charge can be positive or negative, and they understand that protons are positive and electrons are negative. But what's not always clear is that protons are not only positive, they're the only thing in the universe that's positive. And electrons are the only thing in the universe that's negative. If you ever come across an object that is positively charged, it's because that object has protons. And if you ever come across an object that's negatively charged, it's because that object has electrons. So protons and electrons aren't just two things that happen to have charge. They are basically the reason for charge. Everything that has charge has either protons or electrons, and that's what gives it its charge. Now, if you've dealt with charge much before this point, it likely would have been in the context of chemistry, where if we're talking about the charge of, say, an ion, we're looking at something that has maybe 1 or 2 or 3 extra electrons, or is missing 1 or 2 or 3 electrons. So in a context like that, we quantify charge or we measure charge by just counting the number of electrons that are extra or that are missing. So we haven't really had to come up with a proper unit for charge, we just count electrons. In physics, though, we're going to be talking about amounts of charge that are much, much bigger than this. We're not talking about a couple of electrons. We're going to be talking about thousands or millions of electrons. So suddenly, quantifying charge by just counting electrons doesn't really seem sufficient anymore, and we're going to have to come up with a proper unit for it. And the unit we use for charge is called the coulomb. And the symbol for coulombs is a capital letter C. So now that we have two ways to measure charge, we can count electrons or protons, or we can measure charge in numbers of coulombs, it's going to be pretty important that we know how to go back and forth between these two ways of measuring to essentially convert between these two units. So to do that, we're going to need to know the charge on one proton or one electron. And this is a number that we're going to use very often. So it has its own letter that we use to symbolize it. And that letter is E. So E stands for the charge on a single electron or a single proton. And it is 1.60 times 10 to the power of negative 19 coulombs. So this negative 19 here tells us that this is a very small number. The charge on a single electron or proton is a very small number of coulombs, much, much less than 1 coulomb. So conversely, the number of protons or electrons it takes to make a charge of 1 coulomb is going to be a really, really, really big number. And just like to save ourselves from always having to write 6.67 times 10 to the power of negative 11, we just use the symbol G. And to save ourselves from always having to write 3.14159, etc., we use the symbol, the Greek letter pi. To save ourselves from always having to write 1.6 times 10 to the power of negative 19, we just use the symbol E. Now, common misconception here is people think that E stands for electron, which is fair enough to think because E is the charge on an electron, but E doesn't actually stand for electron. It stands for elementary charge. Which basically means it's the most fundamental, smallest amount of charge you can have. It is the charge on an electron. It's also the charge on a proton. And you can think of this, like I've said before, as sort of the building block of charge. Since all charge in the universe comes from electrons or protons, and electrons and protons have this many coulombs of charge, all electric charge in the universe comes from multiples of this number. If you have 2 electrons, then you have 2 times this much charge. If you have 10 electrons, you have 10 times this much charge. Okay, so that gives us a basic understanding of electric charge. Why is this so important to electric circuits? Well, electric current, which is the key thing that we have in electric circuits, is a measure of the flow of charge. So once we have charge that is now moving, we have electric current, which is the next quantity we're going to talk about. So when electric charge is moving, we say there is an electric current. Which has the formula I equals Q over delta T. So the I here is the symbol for current. Q is the symbol for charge, and it's measured in units of coulombs. And T, as we know, is the symbol for time, which is measured in seconds. So looking at this, we can figure out the units of current. Since current is charge divided by time, and charge is measured in coulombs, time is measured in seconds, the units of current should be coulombs divided by seconds, or coulombs per second. And there's another way of saying coulombs per second, and that is amps. Or just a capital A is the symbol for amps. And another thing that's worth noting about electric current is that electric current flows from high potential to low potential. Remember, potential is a word that is very similar to potential energy, but it does mean something slightly different. If you can remember the ski hill analogy I like to use, potential was like the height, on the ski hill. So saying that current flows from high potential to low potential is sort of like saying skiers on the ski hill go from high height to low height. They go from high up on the hill to lower down on the hill. After current, the next two quantities I want to talk about are voltage and resistance. So voltage is the difference in potential across part of a circuit. And it has units of volts, or just a capital V for short. And at this point, I think it would be useful to just draw a very simple circuit to help illustrate some of the ideas I'm talking about. So sort of the simplest circuit we could imagine would be one that has a power source, some wires, and then a single device, maybe a lamp, maybe a heater, maybe a motor, and then wires that bring us back to the power source. That's sort of the simplest circuit I could imagine. And remember, the ski hill analogy can be useful here. With that analogy, this power source is a chairlift that lifts skiers up, gives them potential energy. These wires are cat tracks. They can ski along where they don't really have to slow down at all. They're not losing any height. And then this resistor is a ski run with some trees, some moguls. It requires them to use their edges. It requires them to slow down. And as they go down it, they lose a bunch of height. They lose potential energy. Then we have some more cat track at the bottom that brings them back to the base of the chairlift where they can repeat the whole thing. So when we say that voltage is the difference in potential across part of a circuit, there's a couple places where we could talk about that. This part of the circuit here will have a difference in potential. Just like the chairlift will have a difference in height from one end of the chairlift to the other. And this part of the circuit over here, the resistor, will also have a difference in potential. Just like when you go down a ski run, there's a difference in height between one end of the ski run and the other. That's what we're talking about when we talk about voltage. The difference in potential across a device on the circuit. Now, resistance is sort of how difficult it is for current to flow through part of your circuit. And resistance has units of ohms. And the symbol we'll use for that, well, it's kind of convenient. There's a Greek letter that sounds a lot like ohms, and that's the Greek letter omega. And the capital omega looks like that. Okay, so with all of this in mind, let's go back up here and look at our simple circuit example. We started talking about charge, and there is electric charge in the wires and in the resistor and in the power supply everywhere on this circuit. And fundamentally what electricity is it is that charge moving. And when the charge moves, we say that there is electric current. So there will be current at all points in this circuit. The current, you'll remember perhaps, sort of leaves the positive terminal of the power supply and heads out in the circuit that way. We use the letter I for current. So that arrow there shows us where the current's heading. And I've drawn the current here, but there's going to be current along here and through the resistor and down here. The entire part of the circuit will have current in it. The next thing we talked about was voltage, which is the difference in potential. And so there will be a voltage here at the power supply, just like there's a difference in height across a chairlift from the beginning to the end. The other place where we'll have a voltage is over here by this resistor. There'll be a difference in potential from one end to the other end of that resistor, just like there's a difference in height from one end to the other end of a ski run. And the last thing we talked about was resistance. And the only part of this circuit that has any resistance that tries to slow the charges down at all is the resistor. So we've got a circuit that has charges everywhere throughout it. Once those charges move, it has current everywhere throughout it. There's voltage at two locations, the power supply and the resistor. And there's resistance at only one location, and that's again at the resistor. And also remember that it's the long line of our power supply that's considered the positive terminal, the short line that's considered negative. And so our current, which is the flow of imaginary positive charges, would be repelled by the positive terminal on our power supply. So current leaves the positive terminal. Okay, so this brings us to the next thing we want to talk about, which is a formula that ties all of this stuff together. And that formula is Ohm's law. It tells us how voltage and current and resistance are all related. And it goes like this. V equals I times R. Now, when you apply this formula, you can't just apply it to an entire circuit. You have to pick part of the circuit to apply it to. And it's going to have to be a part of the circuit that has a voltage, that has a current, and that has a resistance. So, if we think, well, what part of our circuit has a voltage and a current and a resistance? Well, that would be the resistor. So that formula I've given you doesn't really work over here at the power supply. It doesn't really work over here on a wire. The only place it works is where we have some resistance, which is going to be at a device like a light bulb or a heater or a motor, etc. So once we've picked a device and said, okay, this is the device we want to apply Ohm's law to, here's what each letter in that law means. V is the voltage across the device. And the units there are going to be volts, capital V. I is the current going through the device. And it's going to be measured in amps. And R is the resistance of, or the resistance in the device. and it's going to be measured in ohms. Okay, so now we understand a little bit about charge. We understand how it's related to current. We understand about voltage and resistance and how those are all related. Let's do a couple of simple example problems. First example is just about charge. And it says how many electrons are needed to make up 3 coulombs of charge. Remember, all charge in the universe comes from either electrons or protons. 3 coulombs is a fair bit of charge, so we're going to need a lot of electrons or protons to make this. Now, it's worth noting that because electrons are negative, they would make up, you could use electrons to make negative 3 coulombs of charge. So maybe I should be a little more particular and write negative here in front of the 3 coulombs. But we can just think of 3 coulombs as being sort of the magnitude of the charge. Anyhow, fundamentally what this question comes down to is just comparing 2 different ways to measure charge. We can do it using coulombs, or we can do it by counting electrons or protons. And this is what we talked about right up here in the lesson, first off, about this number here, the elementary charge, which was the amount of coulombs on a single electron or proton. So to tackle this example, we're basically doing a unit conversion is how I want to think of it. We know the amount that we know we have is 3 coulombs. So I'm going to write that over here on the left as a fraction, so over 1. And the quantity I want to get to is going to be not in coulombs, but in electrons. So I'm going to write that over here on the right, also as a fraction. And I want to try and get from the left side to the right side. I'm going to do that by using a conversion factor. And the whole idea with this conversion factor is I want to get rid of these coulombs that are on the top. And I'm going to do that by putting coulombs on the bottom. And then I want to make sure I end up with electrons on the top. So I'm going to write electrons here on the top. Now to make this conversion factor work, I just need to come up with numbers for the top and the bottom. I basically need a number of electrons and a number of coulombs that are actually the same amount of charge. And that's where the elementary charge comes in. We know that 1 electron worth of charge is 1.6 times 10 to the negative 19 coulombs worth of charge. So to solve this problem, I can just go 3 divided by 1.6 times 10 to the negative 19, and that gives me, if I round to 3 sig figs, 1.88 times 10 to the 19 electrons. So that is a lot of electrons. And it's always good practice when we are doing our unit conversions to make sure everything's sort of canceled out nicely. I have coulombs on the top and on the bottom, so they'll cancel out. And then unit-wise, that leaves me with electrons. Whoops. Leaves me with electrons on the top, and then just a bunch of ones everywhere else. So that should leave me with just electrons as my units, which is what I wanted. So let's have a look at this next problem now. An electric fan has a resistance of 12 ohms and requires 0.75 amps of current to function properly. What voltage is required to operate the fan? So if we are given a resistance and we're given a current and we're asked for a voltage, that sounds a lot like a problem where Ohm's law might help me. Resistance, current, and voltage. So let's put Ohm's law down here and see what we can do with it. We don't need to rearrange anything because V is already isolated. The current I is going to be 0.75. The resistance R is going to be 12. Those are both already in nice metric Bates units. So 0.75 times 12 gives us 9. And that's the voltage. Units of voltage are volts. So 9 volts exactly is the answer. And one of the things that's going to just take a little getting used to with these problems is trying to figure out what numbers you're being given, V, I, R, C, etc. This question was fairly straightforward because it told us that we were being given a resistance and a current. But even if we hadn't been given those words, we would still know that this 12 was a resistance because the units were ohms. Anything in ohms is going to be a resistance. Anything in amps is going to be a current. And anything in volts, obviously, is going to be a voltage. All right. Now, I led off this lesson talking about charge. I said fundamentally what electric circuits are is charge that's moving around. That's sort of what they are. But what they do, or why we have them, is more about power. Electric circuits are all about transferring energy from one place or from one form to another. An example I often like to think about is a flashlight, one of the simplest electric circuits you can imagine. The whole purpose of a flashlight is to take the energy that's in the battery in the form of potential energy and transfer that energy from the battery to the bulb and transfer it from potential energy into light energy at the bulb. That is the whole purpose of the flashlight and of the electric circuits inside it, to transfer energy from one place to another and from one form to another. And you might remember that the transfer of energy from one place to another or from one form to another is called work. So that is what our electric circuits fundamentally are trying to do, is they're trying to do work. They're moving energy around. Now, often in circuits, it's important to know how fast this is being done, how fast energy is being transferred. For example, a flashlight doesn't require a very fast transfer of energy. Doesn't use a lot of energy. But an electric car would require much more energy to be taken out of the battery at a much faster rate. Same with an electric heater, if you compare them to a flashlight. So the rate at which energy is being transferred is really important when you're designing an electric circuit. And this rate, the rate at which energy is transferred, or the rate at which work is done, you might remember, is called power. Power is the rate at which work is done. And there are two formulas for power that will be useful for us when we're dealing with electric circuits. One is a formula we've learned before, That's the definition of power. Power is work over change in time. This formula works all the time when you're dealing with power. This formula always applies in every situation that involves power, because this formula is basically the meaning of power. Power will always obey this formula. Now, the second formula doesn't apply in every situation where we have power. The second formula only applies to power in electric circuits. And this formula is P equals V I. So anywhere in an electric circuit where you have a voltage and where you have a current, there will be power. There will be energy being transferred in one way or another. So let's think about places in a circuit where we have power. Well, we've got current everywhere, remember? So where do we have voltage? Here at the power supply, and here at my device, at my resistor. So at those two places, at the power supply and at my resistor, there will be energy being transferred. At the power supply, energy is being sort of added to the circuit, and at the resistor, energy is being taken away from the circuit, you could say. And then I just want to give you one quick reminder that the units of power are watts. So let's tackle an example here. An electric heater emits 1 times 10 to the 2, so 100 watts, when connected to a 120 volt power line. What is the resistance in the heater? Okay, so we have here an electric circuit that is doing what all electric circuits do. It's transferring energy. It's taking energy from the 120 volt power line and it's transferring it to this heater where it's being transferred into thermal energy or heat at the rate of 100 watts or 100 joules per second. And we want to know something about resistance. Well, these first two numbers I've given, here's something in watts, so it's a power. Here's something in volts, so it's a voltage. What can I do with power and voltage? I can use the new formula that we just got. P equals VI. And the thing I can do with that is I can isolate I and solve for I. So I is going to be P divided by V, which is going to be 1 times 10 to the 2, or 100. That's in watts, so metric base units, that's good. My voltage is going to be 120. That's in watts, or in volts, so also metric base units, also good. And this gives me 0.83333 repeating. And I've solved for current. The metric base units of that are amps. So far I've taken a bit of an odd approach to this question. I haven't even really looked much at what it's getting me to find. I just said, well, I know power and I know voltage, and sort of the only thing I can do with those two things is use this new formula I have. But now let's look at what we're being asked to find, and that is the resistance. So how can I solve for resistance? Well, the only formula we have with resistance in it is this guy up here, Ohm's law, V equals IR. So let's see if we can use that. If I rearrange this to solve for resistance, I get R equals V divided by I. And I think because of the work I just did, I know both V and I. The V is 120 and the I is 0.83 repeating. So if I plug that in, I get 144 ohms. And so that's the idea with today's lesson. We're not doing a ton of real critical thinking here or trying to solve any major conceptual problems or even any major sort of multi-level problem solving. We're just trying to understand some of the basic quantities we have to work with, recognize the units that they use, and become familiar with some common simple formulas we can use for sort of relating them all to each other.